Today we're starting a new section in the book, and this is transportation planning. This comes from chapter 8 out of the book. And transportation planning is kind of the big picture, and we've worked before, I guess, starting on smaller roads and looking at transportation processes and how traffic flow happens and what our capacity is on traffic signals and so forth and so on. Now, this bigger picture is if you build new roads or if you do new things, what's going to happen through that. And so, again, we're kind of taking one step back, a little higher view of transportation, and particularly of road use. Through that, the book just focuses mostly on the highway side of it. But we use travel demand modeling for all modes of transportation. We'll talk about that a little bit here in a second. So we'll talk today about the four-step travel demand model. It's the classic four-step model. We may talk about that and also dig into a little bit more as we start understanding, I guess, how it works and how we use it from that. Travel demand modeling, like I say, it covers a lot of different scales, and so we can look at future volumes on roads, we can do ridership on transit services, we can model growth within a city or region, we can look at, if we add in roads and other new railroad lines or routes, new bus lines, so forth, we can model that, and the idea is will people use it, and if so, how many? It's kind of the questions we ask for that. Here's an example. From the backside of the Mire, which is now here and wasn't before. This was a real project a few years ago the city had talked about was, well, what if we connected across from this shopping center here where the Mire is, across the railroad tracks and up into these subdivisions back here. And you can see it over here on this side a little better. And this has all been built out now. There's a bunch of apartments back in here, and obviously Mire has built out more through that, and so it's a very busy area, and the city was thinking, well, there's no other good link north-south through here between State Road 2 and these areas to the north, and then the shopping center, and except coming all the way back over to Silhavy through that, and so why not? Maybe this would be a good link to build. Right? And how do you know? How do you know if it's going to be a good link? How do you know if people are going to use it? Is it useful? So those are the questions that travel demand modeling tries to answer, and that's what we use it for. We use it for this long-range plans. Travel demand modeling, the local MPO, the local Metropolitan Planning Organization, they've got plans starting, I think, about every 5 years. They have one updated for that, and it goes right now. I think their current one is to 2055 or something like that. So it's 30 years. In the future, obviously the results, the model, isn't as accurate the further you get out from that. But they do it. The point is they do it for pretty long range planning. And the idea is as you're building new infrastructure and building new roads and thinking about your community as a whole, where do you want to see new routes? And if this route was here, how would it behave as traffic grows or as development expands over the next number of years going ahead, right, from that. Chapel Drive used to go all the way through campus. Here would be an example, I guess, closer to us. So here's Chapel Drive. This is back 15 years ago or so. And then they decided, well, they didn't want the cars driving through campus anymore, so they cut it off. Right. So now this is what we've got. And you see, that's one of the reasons we have weird sidewalks through there, is they used to follow Campus Drive through that. Where did that traffic go? So where do you think it went? Right. So if people used to be driving through the center of campus, from that, and we had parking out here in the front. If people were previously driving through the center of campus and now that road is gone, then that traffic that used to cut through has to find other routes through there. And so where did it go? And that's what, it's one question travel demand modeling should hopefully answer for that. And it's probably going on these peripheral roads around here, around the outside edge of campus. People have to use that now to get around more. And if you were cutting through before from one side of campus to the other, obviously you're going to have to come out now either to LaPorte or down to US 30 and so forth and pass around there. And so those are the kinds of questions that travel demand modeling tries to answer from that. So what would you need to know? This is, if we were in class, we would have this discussion on what do you think you need to know to be able to model where cars are going to be in the future, or what change in a roadway network is going to do to the traffic volumes, particularly of the roads around it. So, do we need to know how many cars were on the original route? Yeah, that's probably helpful. Would it be nice to know where people who used to be driving through this route, let's say, where they were coming from and going to? Yeah, probably. You know what makes people drive? What causes traffic? And be, I guess, a larger question to ask. And I don't know. I'll give you the answer. The answer is typically people are going somewhere they want to go. And in travel demand modeling, what we found over the years is that if you can figure out what people's purpose was for their trips, we can do a better job of trying to figure out how many trips are being generated in our demand models. People going to work, that's a pretty classic one, right? And we assume that they're going to go to work in the morning and come home in the evening, especially if it's an office type job. And from there, we can kind of figure out where people live because we know where the residential districts are in the city, and we know where the employment centers are. So Valparaiso University would be an employment center, and everybody who works here has to get here somewhere, right? The students live on campus, but the faculty and staff don't. So all the faculty and staff, wherever they're living, we'd say, well, they're going to be making trips into campus in the morning and leaving in the afternoon or evening through that. Students, where you live, right? So if you live up here in Beacon or some of these other halls, right? We know where you live, and we know your classes are over here in Galveston, and so we could map that across from where the dorms are to where your classes are, and say, well, these sidewalks in here are probably going to be busy because a lot of students live, in the Berg or alumni or wherever you're coming from. If you live there, if we know what dorm you're coming from, we can kind of guess what sidewalk you're going to use to get into Galveston. That's the same idea as travel demand modeling. If we can figure out what district people live in or where the most dwellings are, the most homes in our apartments, and where the most employment centers are, where the most business centers are, and the most retail, where there's enough jobs, we can kind of start mashing that together and figure out what routes people will take. And traditionally, this has been done in a 4-step model. You'll hear this talked about off and on if you go to conferences and whatnot. Planning, you'll hear about the 4-step process or the 4-step model. And this is the classic one. And our book actually cuts one of these out, so I don't know why, but they decided we didn't need mode choice. The book only looks at roads. But it's typically trip generation, which is in a certain housing district, because we know where houses are geographically in our area. This house, how many trips in general would that house take, right? Think about it. How many trips do you take out of your dorm room or wherever you're living, your apartment, each day? So that's trip generation, right? If I look at my house, I take a trip to work every day and I come home every day. So those are 2 trips. And occasionally I guess I drive to the store. So that would be a 3rd trip, not every day. So my trip generation is somewhere like 2.1 or something would be the average during a weekday. So occasionally I take an extra trip once I get home, but not usually from that. So that would be trip generation. And then trip distribution is figuring out where people are going. So we know that there's this many trips, but now where are they going? So that would be trip distribution. How am I going to get there? That's mode choice. Am I going to walk? Am I going to ride the bike? Am I going to drive? And am I going to take mass transit? So those are mode choices. That's a mode of transportation I'm going to use for that. And then once we know how many trips each household is producing, where they're headed, and how they are getting there, then we assign them to routes. And it could be a road, a street. So if you're driving, that would be the trip assignment, or it could be a bus line if you're taking mass transit. So those are the 4-step processes. That's the classic 4-step process from that. It hasn't changed too much. And let's say if you study transportation more in the future, you're definitely going to hear more about this. From that, this is what the book shows in their chapter 8. They just kind of cut out, I guess trip distribution they called it. This is really more distribution here. They're saying everyone's going to be on the highway because the book, I guess, only focuses on highways. So that's a default, I guess, of our book. So they've only got the 3 steps, but you're starting somewhere and you're ending up somewhere with traffic assigned to certain roads. And so that's the route choice piece, right? And so that if we put those side by side, that'd be our 4-step model versus the book's version of that through there. You can also look at it linearly, like if you just looked at your day activities, right? So at 6-something a.m. You leave for work, then you go to lunch, that's another trip, then you return home, then once you're home, you head out to go shopping, and then you return home again, and maybe you visit a friend in there. So you could look at it as a timeline like that, and each of these is a different trip from that. So we have work-based home, which is leaving to go to work and then also actually returning. It's the same trip type, but it's two separate trips. From that, going to lunch is also a work-based other trip, we'd call that. So it's another type of trip and so forth. So every time you're leaving your home or moving, I guess, across the face of the earth, then that's a trip. And we would like to, if we could, we would like to be able to model that so we can do a better job on that. And so the question is, on that, we were bound down to how many trips do people take and what kind of trips do they take. It's, we can ask ourselves, do you guys take the same kinds of trips as your parents do? Right? Does your day look the same as your parents? Probably not. You're going to go to class. You're going to go to class at odd times. You're not going to go always in the morning and be there by 8 for your job and then come home at 5. You're to and from class on Tuesdays and Thursdays. Your trip may look different than on Monday, Wednesday, Friday, and so forth. And as me as a professor, do I make the same kind of trips as someone who works at a store? No, right? My trips are different through that. And the times I travel are different from there. So in trip generation, this is like, say, step one is how do we segregate what we're looking at, the data, into uniform enough pieces that we can make predictions, right, from that. And so that's our question, right? Is we are, right? Should we lump together students with professors and with your parents and maybe a more traditional job, right? In how they make their trips? No, we probably shouldn't. And if we can pull those pieces out and look at them individually as a unique kind of types of trips or unique households, that's going to help. That's going to help us start modeling. If I know that in one area that everyone is a student, it's a lot easier to model their behavior than if half people are students and half people work at Target, let's say. Right? So that's very different kinds of probably travel patterns. So it's going to be harder to model. If we can classify, I guess, areas and locations into I guess more typical breakdowns, then we can start looking at that and start doing a better job of modeling about that. So by trip types is how we like to do it. And so if we know people are going to work, that's a more consistent type of trip, right? If we know you're going to go shopping, we know there's a lot more variation in that because people shop in different places through there. We can also break it down by household type, and it could be by age of the residents. It could be by the income level of the residents. Lower income people tend to have fewer vehicles, and so they don't make as many trips, or they make different types of trips and do more trip chaining, multiple trips in a row when they're out. Through that, they may use more mass transit and so forth. And so that's traditionally, these are things that we have seen have made a difference in the number of trip numbers being generated. So this again, we're talking about that. And then also by geography, where is this location? That makes a little bit of a difference too. If you're near a downtown, it's more likely you're going to walk, and maybe you'll take more trips because you just want to go over to the corner store or whatever. If you live out in the country, you might take fewer trips, but when you do, they're going to be longer ones. All right, through that. So we look for these common characteristics we use, and we try to put people into these kind of unique or discrete populations that we can look at through that. And these are some of the ones that have traditionally worked out really well. When we look at our area, we look at the population, right? If there's more people there, they're going to make more trips. So there's that one. We have household type. Is it a single family or is it a multifamily household? Is it an apartment complex or is it, 1 acre lots, out in the suburban settings on that, right? That's going to change the number of trips being generated in an area. Are people employed, right? If you're not employed, you may take less trips, right? So if you're retired, you may take less trips or you may take different kinds of trips. Income makes a little bit of a difference in how many trips people take, how old people are. If you're in your 30s and you've got kids in school, they make a lot of trips. Right? They're driving people all over the place and making more trips from that versus maybe someone who's in their 70s. They probably make fewer trips on that. Modes available, traditionally we'll look at vehicle travel, so you're in your car, but if you have really good mass transit available, it's more likely to use that. So that's modes available. Network capacity, which is how easy it is to get out on the road and use it. Right? And I know when I've traveled through LA that you just never know how long it's going to take you to get even 20 miles because just whatever time of day it is, there just could always be traffic jams, and right, it's either 20 minutes or it's 3 hours. You just never. People don't really know. I guess that's probably exaggerating a bit, but there's that's a famous example of less network reliability on that for travel. Through that, and then finally vehicles per household. That's a good indicator also of number of trips. If you only have one car and you're sharing it between 5 people, that limits the number of trips, at least by car, that people are going to take. If you've got 5 cars for 5 people, people are going to take more trips from that. And we can do this, we can set up an equation for that. And so it's kind of just linear regression is how they work on these. They do surveys and they track people, and then they can come up with these kinds of equations. And the idea is the total number of trips being created in one household is going to be some base amount and plus some coefficient times one of the predictor variables we've got. And plus another coefficient times a predictor variable, plus another coefficient times a predictor variable. And they do, curve fitting to get these coefficients, and then we've got our predictor variables through that. And these could be, so this one could be income, this could be the number of cars in the household. So this one, next one down, next Z could be, are they employed or not? The next Z down is what's their age bracket, and so forth. And so then we can set up these equations like that. And that would tell you for one household with those characteristics, that's how many trips we expect that one household to make. If there's 10 households in that subdivision, then it would be 10 times that trip generation if they were all had the same characteristics like that. Right, from that. Here's an example, right, for shopping trips. So this is home-based shopping. We do a linear regression, tells us that shopping trips a household makes is equal to 0.2, that would be our base coefficient, B naught, plus 0.1 times the household size. Household size is how many people live there, plus 0.02 times the household income in thousands of dollars, plus 0.1 times the number of vehicles owned in that household. And we get an equation like this. So we take this as our general form of it, and we'd end up with our shopping. This is the number of shopping type trips made. This is different from going to work type trips. So this is shopping trips. For every household there, just our coefficient starts out at 0.2 for that. And then if there's 5 people living here, we'd take 0.1 times 5. So we get an extra 0.5 out of that. Income level broken down by the thousands. And so if their household income is 50,000, right, we take 50 times 0.02 plus finally how many vehicles they own. If they own 2 cars, it's going to be 0.1 times 2. All together, that's our predictor for the number of shopping type trips that one household is going to make through that. And so we can plug that in, right? So for a household with 3 people and an income level of 50,000 and 2 cars, we can plug all this in. So there's our base coefficient, and then we're just plugging all that in for our B's and our Z's, and we end up with that. A household like that is going to create about 1.7 trips on average per day, when shopping trips. Right? And so then we would also look at work type trips, and we would look at school type trips, and we'd add that all together, and that would be a total number of trips by that household for a single day. So this is just the shopping portion of it. So again, it's easier to map things by their goal or what they're aiming to do. And so we broke this down into shopping for this case. So if we break it into smaller pieces, it's easier to solve. So that's what we're doing. We're solving one piece at a time, and we add them all together and superpositioning to get our total number of trips from that. So that would be one household. Now, if I had 5 houses with those same characteristics, 3 people, 50,000, and 2 vehicles, I would, in my district I'm looking at, or my zone, I would take 5 times that number, and for that zone, that's the total number of shopping trips for that zone that we look at. So that's key. This is only for one household and just for shopping. And then again, for however many households you have in your subdivision or your whatever size zone you're looking at, you'd multiply that by the number of households with the same characteristics from that. Your ICA will give you some practice with that. So just remember you have to multiply by that full number on there. So if we're looking at those trips, right, how we break them down, and we do by trip types, and so we do it by what's the goal of people's trips, and then we also do by the household types. What's the number of people, income, and so forth. Some of those predictor variables we used. And then finally we look at geography. Where are these people coming from and going to? We want to be able to map where these paths are, people's trip paths, onto a map eventually, because we need to be able to predict how many cars are going to be on a link on the road through that. So geography is important. And so we're going to do this all, we actually start there. We start with geography, and we do our transportation analysis zones, our TAZs, right, from that. And we're just going to split those up through there. What makes a good TAZ? We don't want too many people in it. So between 1,200 and 3,000 would be the number of residents in there. You want less than 15,000 trips a day, otherwise it kind of becomes unwieldy. A quarter to a square mile works really well. I guess in very rural zones, we could use much larger ones. Right, from that, where you want more detail, where you want to be more accurate, you're going to use smaller zones. It's kind of like finite element modeling. You use a smaller finite elements. If you want higher accuracy, we do the same thing in TASs from that. So as we increase zones, though, it increases the complexity of the model. It's harder to get the data all put together, and it takes longer for your software to compute it. Then, and so that's the downside, right? It's a little harder to do if you have more zones, but you're going to get a more accurate number. So you'll blend in the sizes where you don't need much detail. You make big zones to keep the calculations down, but where you do need a lot of detail, then we will make much smaller ones, right, from that. We try to make them kind of squarish around. We don't want long, skinny ones through that. That doesn't model well, and so we like to keep things more of that square or round shape. Right, from that, and then we model things through centroids. Here's an example of a small city and the zones they're using around it. And you can see out here in the suburban areas, we're assuming that the density of housing is less out here. We use bigger zones. Near their downtown of this town, they're using small zones through that because they want a little more accuracy. And plus it's probably a little denser in habitation. More people want to write in there. And so that's an example of that. Right? So larger zones out in the rural areas, and then smaller zones where we need it. We usually line them up along highways. We use those as boundaries and/or rivers, and so we quite often will split our zones right along those major paths, and it also helps the modeling right from that. Here's an example: Chicago Regional Planning Commission does a regional model, a really large regional model. And so they're not going to be super accurate. They're looking at like interstate flows. They're not looking at local street flows. They can build another model, which is much more detailed there. And so they're trying to actually capture everybody who may commute into Chicago and commute back out of Chicago. And so that's why they're covering, the Northwest Indiana, the region is also included in their zone. But they don't need to be too accurate because they're really just worried how many people are headed south on I-90 in the afternoon, in the PM peak, headed back home. And these zones are big enough to be able to model that. So you can see where they didn't need that much detail out here, so they're going to use really large zones out there. Here's Valparaiso. So I guess we have more people in town who are commuting, so they gave us our own little zone around there. And you can see as you get closer to the loop in downtown, then the zones get smaller and smaller through that. And where there's others, cities, Naperville, Elgin, and so forth, they'll use slightly smaller zones out there as well. So they want a little more detail on that. So there's an example of that. Here's the downtown loop. They're using smaller zones in here, and their local model would be even smaller than this probably for the loop, but this is working good for their regional model. And then, like I say, they even got Valparaiso has their own little model on that. So that's our introduction to travel demand modeling in your ICA now. You'll be calculating, you have a little table. You'll be calculating what in fact, I can pull that up. You'll be calculating what your travel demand models are, and I'll just give you some hints here since we're not in class for that. And so you're going to use that equation we just had. And so here's that T is equal to B0 plus B1 times Z1 plus B2 times Z2. That's the equation you're going to want to use for this. Here's your B0, 0.2, and it's 0.3 times the household size plus 0.2 times the number of vehicles. And here's a table, and in this table, if we look at this first point in here, our household size is 1, and the vehicles is 0, and there are 5 households, that's how you read this, there are 5 households with those conditions that have one person living there with no vehicles. There are 12 households that have one person living there with one vehicle. There are 7 households with one person living there and 2 vehicles. Right, and now you're going to go through and calculate your total trips. You're going to take 0.2, let's do this first cell, 0.2 plus 0.3 times the household size. What's my household size? 1, plus 0.2 times the number of vehicles, which is 0. And so in this case, I got 0.2 plus 0.3, that's 0.5. I have 5 households like that, so I'm going to take 5 times 0.5, right, and I'll get 2.5 total trips coming from just that cell. Then you're going to have to do that for each of these others. Do that, and then finally sum them all together, and so this zone would have a total number of trips of X, whatever that is. So there's your hint to get started. Good luck on that.